Hi everybody, and welcome to our notes on atomic theory and counting atoms. This unit goes along with chapter 3 in your textbooks. What we're going to be learning about include these subtopics. So first we're going to talk a little bit about the history of atomic theory, and we'll learn about the different subatomic particles. Hopefully this is a review. A subatomic particle is a particle that's inside of an atom. We'll learn about atomic number, isotopes, and mass number. We'll learn about the law of conservation of mass and do a lab on it, and then we'll learn about the mole. The first three bullets are the ones we're going to focus on for today's lesson. The learning objectives for this unit include being able to compare and contrast protons, neutrons, and electrons, explaining the law of conservation of mass, explaining the relationship among isotopes, atomic number, and mass number, explaining the difference between molar mass and atomic mass, and be able to solve problems involving mass in grams, amount in moles, and number of atoms. And finally, next to understand the mole and Avogadro's number, and describe how scientific discoveries built upon each other to build our present atomic theory and what we understand about the atom today. So we're going to talk a little bit about atomic theory history. We'll learn about some Greek philosophers, John Dalton and Ernest Rutherford. You do not need to take notes on the Greek philosophers, but you will need to write down John Dalton and Ernest Rutherford. To begin with, let's remind ourselves what a scientific theory is. A scientific theory is a statement that helps explain a wide variety of facts and laws. It is kind of in the hierarchy of scientific thinking. You have facts, you have laws, and then you have theories. So they are an overarching idea that helps explain a lot of different things. We talked a lot about that during our evolution unit last year in biology. So for atomic theory, let's say I had this piece of paper right here, and I ripped it in half. And then I ripped it in half again. And then I ripped that one in half. If I kept ripping, would I ever end up with the smallest piece of paper? Or would I keep ripping and ripping and ripping and ripping and ripping forever and ever and ever and ever and ever? That's the question that people asked when they were thinking about the stuff around our world. So these questions, can you ever get to the smallest piece of matter? Developed into theories about the stuff that makes up the world around us. Now, the first person to really think about this is Empedocles. He was a Greek philosopher and scientist around 450 BC, and he was one of the first to propose that things around us are made up of other things, which was important. And what he said was all matter is made up of 4 elements: earth, air, fire, and water. His theory was important because it was really the first scientific thinking that suggested some substances that look like pure substances, like stone, are actually made up of a lot of different elements. And we have a little picture here that kind of seems silly to us now. We have this bunny rabbit. He's made up of fire, air, water, and earth. And I guess there's a little bit of truth to it. If you think of fire as energy, air as oxygen and carbon dioxide that's inside of us, water definitely is inside living things, and earth is as the atoms that make up living things. You can think of it that way. Democritus was another Greek philosopher after Empedocles around 430 BC. And he had a very interesting theory. He said that matter could not be divided into smaller and smaller pieces forever, that eventually the smallest possible piece would be obtained, and that this smallest possible piece couldn't divide it anymore. And he named this smallest piece of matter atomus, meaning not to be cut. And hopefully you see a pretty important chemistry word inside of our atomus word there, word atom. To Democritus, atoms were small, hard particles, and they were all made of the same material, but were different shapes and sizes. He said the atoms were infinite in number, always moving, and capable of joining together. And this theory was ignored and forgotten for more than 2,000 years. So he was indeed pretty accurate, especially for the time, saying that you could get to the smallest piece of matter. You could get to this thing that you couldn't cut, called this atomus, which we know of today as atoms. Another atomic structure thinker was Aristotle, and you've probably heard of Aristotle before, and his idea was that all matter was continuous, and it was accepted for almost 2,000 years. His ideas were not supported by any data whatsoever or evidence, and they were wrong. So what is it that you think made people believe Aristotle or follow him versus Democritus? Think about it. Why would they understand and follow Aristotle's idea instead of Democritus, who was actually the one that was more correct? Okay, so we're going to jump ahead and make some progress to the 1700s. And at this point in time, all chemists did accept the idea that an element was the smallest you could get, an element. They believed an element could not be broken down into smaller sections, and we know today's definition of an element is a substance that cannot be broken down into simpler substances. It's the simplest type of pure substance. And the other thing you could add to this is that it is made up of one type of atom. So a carbon element is made up of only carbon atoms. Iron element is only made up of iron atoms. Now here's John Dahlen, and he was an English school teacher in 1808, and he came up with 5 postulates to his atomic theory. You need to write these down and know them. The first one is that all matter is composed of small particles called atoms. The second is that atoms of a given element are identical in size, mass, and other properties. Third, atoms cannot be subdivided, created, or destroyed. 4, atoms of different elements combine in simple whole number ratios to form compounds. And number 5, atoms are combined, separated, and rearranged in chemical reactions. Okay, so make sure you have all 5 postulates down. If you need to pause, do so. The other person we're going to talk about is Ernest Rutherford. Ernest Rutherford conducted a gold foil experiment. If you think of aluminum foil, sometimes you might call it tin foil, aluminum foil, well, he used the same foil, but it was made up of gold atoms instead of aluminum atoms. And what he did is he fired radioactive particles, these alpha particles, through thin gold foils. And what he found was that most of the particles passed straight through, no problem. But about 1 in 8,000 were deflected. So they must have had something happen to them where they were bounced back to where they were coming from. So some of the conclusions he drew from this was that his theory was that most of the atom was empty space, and there was something inside of it too. So here's kind of a picture of what this looked like. So here's our alpha, or radioactive particle emitter, and it had this detecting screen around it, and he fired these particles at this piece of gold foil. And most of them just went right on through, but a few were deflected back out. 1 out of 8,000 were deflected back out. So his conclusion said that the atom has a small, positively charged and dense nucleus with protons and neutrons. So these particles that bounced back had to have hit something along the way. That's why they changed directions. Otherwise, they'll just keep going and going in the same direction. And that the remainder of the atom is mostly empty space and electrons. So if you need to remind yourself, pause this and answer question 4 on your What's Inside activity from class today, answering that question about Rutherford. Okay, that leads us into our last section that we're going to do today, which is on atomic structure: protons, neutrons, electrons, mass number, atomic number, and isotopes. So first, let's remind ourselves of what atoms are. They're the smallest unit of matter. They are made up of subatomic particles. So those atoms that are those particles that are inside of an atom are electron, proton, and neutron. Hopefully you know some things about each of these. A proton is positively charged. These things are very important because they determine what the element is. So any element that has 1 proton is hydrogen. Any element that has 10 protons is neon. If it gets 11, it changes its identity. If it has 9, it changes its identity. Protons are found in the nucleus, and they have a mass of about 1 AMU. AMU stands for atomic mass units. Neutrons have no charge. They are in the nucleus, and they also have a mass about 1 AMU. So already you can see some similarities and differences between protons and neutrons. Both of these particles are inside of the nucleus, and they help contribute to the mass of the atom. Electrons, hopefully you know that they are outside of the nucleus. You spent time on this in the past. They are negatively charged. They have an extremely small mass, so when we do mass number, we don't even really count them. And they move around the outside, so they have movement to them. Here's a graphic organizer to help you understand how atoms are arranged. So first of all, there are 2 different spaces of an atom. There's the nucleus as one of them. Inside of the nucleus, we have protons, which are positively charged, and we have protons, which are positively charged, and neutrons, which are no charge, or have a neutral charge. The other area of the atom are the electrons, and these have a negative charge. Some other things to include is to note that the protons and neutrons contribute to most of the element's mass, or the atom's mass, and that the atomic number equals the number of protons. And in a neutral atom, so the whole atom has no charge to it, has an equal number of electrons, which are negative, and protons, which are positive. Positives and negatives balance each other out to give a neutral atom. Okay, let's talk a little more about atomic number. Atomic number is the number of protons in the nucleus. So those numbers are always the same. Each element has a specific atomic number, and this atomic number determines its identity. So like I said earlier, neon atoms have 10 protons, so that makes them neon. If the number of protons change, so does the identity of the atom. Isotopes, these are atoms of the same element, but actually they have different masses. An example of this is carbon-12 and carbon-14. 12 and 14 are their mass numbers. They're both carbon, but their masses are different. So the isotopes all have the same number of protons and electrons, but they have different numbers of neutrons. So neutrons is a thing that varies between isotopes. And the mass number. The mass number is the total number of protons and neutrons that make up the nucleus of the atom or the isotope. So if you have 10 protons and 10 neutrons, your mass number would be 20. If you have 10 protons and 12 neutrons, your mass number would be 22. Now, what you're going to need to know is how to designate isotopes, so how to write them. And there are two general ways to do this. The first way is called the hyphen notation. In the hyphen notation, the mass numbers are written with a hyphen after the name of the element. So, for example, you take the name of the element, like you see here, as uranium, dash its mass number, not its atomic number, it's mass number, the number of protons and neutrons. So uranium-235. The other way of doing this is through a nuclear symbol, which has subscripts and superscripts. The superscript is the top number. This is the mass number. And the subscript, or the bottom number, is the atomic number. And it looks like this. Okay, so again, we're still on uranium-235. And just to write down so you have it, that U, that's the element symbol that comes from the periodic table. 235 is the mass number. 92 is the atomic number. Okay, so two different ways of writing isotopes. Isotopes, again, are elements that are the same type of atom, but have different masses. Okay, so you may be asked to find the number of neutrons of an atom. So if you're given the mass number in the type of atom it is, you can figure out the neutrons. The number of neutrons is found by subtracting the atomic number from the mass number. So mass number minus atomic number, number of protons, gives you the number of neutrons. So if you take uranium-235 as our example, 235 is the number of protons and neutrons. You take away 92, which is uranium's atomic number, the number of protons uranium has, and you get 143 neutrons. Okay? Average atomic mass is the weighted average. So calculating the average atomic mass, we need to indicate the relative abundance of each isotope and the mass of that isotope. So to do this, the equation is, as you see here, you take the mass number times the percent abundance. And you do this for each isotope. Then you add each together. So it's kind of like the way when you have a grading system where your grades are weighted and tests are a certain percentage and labs are a certain percentage and homework's a certain percentage. It's the same idea. So for example, if you have here, neon exists as 3 natural isotopes. Calculate the average atomic mass of neon using the information below. So you have the different percent abundances, so 90.51% of this atom of neon, 19.99244. 0.27% of this one, 9.2% abundance of this one. So to solve for it, you take the mass number, so the 21.9913 or the 19.99244, times the percentage for each isotope. So in order to do this, you need to remember that their percents are out of 100, so you must divide each by 100, or you can also just divide your answer by 100. So continue on. This is the same idea after you do this, 90.51% times percent of the mass, percent abundance times the mass, percent abundance times the mass, and you divide by 100, you should get your answer to be about 20 AMU. Okay? So go back and review any of the concepts if you need to, record any questions you might have, and we'll continue working with this stuff in class next time. See you then.